Let's take a look at energy, work, and power. These are three things that are very closely related, so we're going to cover them all in one big old video with a few practice problems mixed in, so it might be a little bit long, but go ahead and stick with me or you guys can fast forward to whatever section you need. First thing we're going to cover is energy. So energy comes in many, many forms, but in this physics class, all we cover are three of the mechanical energies. We're going to talk a little bit about thermal energy, but that'll come in later. First one that we're going to look at is kinetic. So kinetic is something, if you remember kinematics, it's the study of movement. So kinetic energy happens when things are moving. And the equation for kinetic energy is going to be that Ke, that's our abbreviation for kinetic energy, is equal to 1/2 mv squared, where m is the mass and v is that velocity. So that's the equation for kinetic energy. Again, it happens when things are moving. Potential energy is kind of what it sounds. Think about the word potential. It's things that it could have in just a moment. So gravitational potential is the first type. And just a real quick side is potential energy is a little bit weird. We abbreviate it by using the letter U. So gravitational potential energy is U sub G for gravitational. And the equation for that is mgh, where m is the mass of the object, g is the acceleration due to gravity, and h is the height. So gravitational potential energy exists really anywhere where you have a gravitational pull. In everyday life, we have learned that objects pull towards each other, but that's such a small gravitational pull that we really can just ignore that. But large things like planets, so when you're on Earth, you do have to take into account that gravitational potential energy, or on the moon or Saturn, or if you're ever near that big body, you do have to worry about gravitational potential. And one other weird thing about gravitational potential is that it does depend on some set position. So if you've got, for example, an object that's sitting on a table, you could set the 0 line as the ground, in which case it is this high off the ground, and that would be your h. If you're feeling a little bit weird, or if it makes the problem easier, what you might want to do is set this as your 0 line, which would mean that it has a height of 0 from your 0 line. So we'll talk a little bit more about that, and we'll work a problem out with it. But basically what you have to do is you have to set a 0 line. And typically it's not going to affect anything, depending on where you put that line, it shouldn't affect the problem, but where you put it might make the problem easier or harder. So again, we'll look at that with the practice problem that we've got on the next page. The last one is elastic potential energy. And this one, let me switch to white again. The elastic potential energy is U sub E. The equation for this is 1/2 kx squared, where k is the spring constant, which is something every spring has a spring constant. It's basically how stiff or how loose a spring is. And then x is how far you either stretch it or compress it. So if you think about, if you disassemble the pen that you're looking at, there's a little spring in there. You can either compress it or you can stretch it out. Either way, it always wants to go back to that equilibrium position. So we'll go through and we'll work a practice problem here. So let's go ahead and take a moment, go ahead and pause the video, read through it, just kind of give yourself a little picture of what's going on here. So hopefully you guys took a second to read that. If you haven't finished, go ahead and pause it and then finish reading it, because I'm going to jump right into it now. So the first thing I always like to do is draw out what in the world is going on here. So we've got some person here, and they're throwing a baseball up to a friend that's sticking out the window. So here's the friend being safe, just sticking their hand out the window, not reaching their whole body out. And the general idea is they're going to throw a baseball up, and if that baseball can reach 20 meters off the ground, then the friend can catch it. So I see kind of a before and an after here, which is good because energy is conserved. As long as there's nothing messing with the object, so if no bird comes in, and as long as we discount air resistance and all that stuff, then energy is conserved. Which means all the energy that the ball has from the moment it leaves this person's hand to the moment it comes up to its maximum height is all of the energy it has ever had and will ever have until something comes in and messes with it. So I see those as my before and after. So I'm going to go ahead and label that as, well, no, I'm not going to do before and after. Let's go initial and final, because B and A seem a little bit weird. So here's initial, and here is my final position. So what I'm going to do is I'm going to actually say that my initial energy equals my final energy. And I'm allowed to say that because absolutely nothing happens to the ball between this red line and this red line. As soon as this person comes in and grabs it, then the energy changes. If we didn't discount air resistance, then there would be something happening to the ball and this statement wouldn't be true. So we're going to go ahead and assume that air resistance is negligible here. What I like to do when I'm starting these problems is I'll go ahead and write out all those three mechanical energies that we look at. KE initial, UG initial, and UE initial. And all of those equal KE final plus UG final plus UE final. And now I'll go through and ask myself little questions here. So ultimately, my question is, does the ball reach 20 meters off the ground? So what I'm going to actually do is I'm going to try and find out how high does the ball reach. If nothing were to happen to it, I want to figure out what is that maximum height. And if that maximum height is less than 20 meters, then I know that it doesn't reach the friend. If it's greater than 20 meters, then I know that it does reach the friend. So here we go. Let's take a look at this. The initial kinetic energy is things moving. As soon as the student releases it, it is moving, so I cannot get rid of that. UG is my gravitational potential energy. So this is where I need to set myself a zero line. Most people are going to be comfortable setting it at the ground. That's kind of the default position that you want to set it at. As you do more and more of these problems, you'll actually discover that it's probably easier if you set it in the person's hand, but I don't want to jump to that just yet. Once you get more comfortable with this, come back to the video and see if you can figure out the easier way to do it. But I'll go ahead and set it as the ground because that's where most people like to set the gravitational being zero. So I do have gravitational potential energy here. There is no spring in this problem at all. There's no rubber bands or anything like that, so I know that goes away. At the end, when it reaches its max height, the ball has to be stationary. If it was still moving up, then that wouldn't be the max height. If it was now moving down, then we know that previously it was up. So at its maximum height, that velocity is zero. We are off of the ground, so we do have a gravitational potential, but again, we do not have any sort of spring or rubber band, so that potential energy is zero. Now I'm going to go ahead and plug in. I've got 1/2 mv squared plus mvi plus mghi, that's my initial height, equals mghf. Now, if you tried to start this problem by plugging in numbers, then you'll quickly discover that you don't have enough information. But if you think about it and do a little bit of algebra, you can see that the masses all cancel out. Now that the masses have canceled out, I can do some rearranging, and again, my ultimate goal is to solve for my final height, or sorry, my max height. So now let's go ahead and do that rearranging. I've got 1/2 vi squared plus ghi equals GHF. I can divide both sides by g, which again is the acceleration due to gravity. And I get 1/2 vi squared plus GHI over g equals HF. Now it's just a game of plugging in the numbers and putting it into the calculator. So 0.5, I'm going to change it just to make it easier on myself, times the initial velocity, which is 22 meters per second, plus g, which is 9.8, times hi, it is released 2 meters off the ground, all divided by 9.8 will give me my HF. So give me a moment to plug this into the calculator. I'm going to be very careful with my parentheses so that I don't accidentally make a mistake there. And divide that all by 9.8, and I find out that it reaches a maximum height of 26.69 meters. So I look back at the question and ask, have I answered the question? And the question is, can the friend catch the ball? Well, the maximum height is 26 meters. All we need is 20 meters, so the answer here is yes. And again, the reasoning is because the maximum height that it could reach is higher than what we want it to be. So yes, the friend could grab it on its way up or on its way down. So here's the idea of energy. Again, as long as nothing is messing with your system, then you can say that all of those energies are the same. And then you just go through those three types of energies we talked previously. Go ahead and plug in anything that's zero, just to make your life easier, and usually you'll end up with a much nicer equation. Again, as you do more of these, please try and do this problem, maybe putting the zero line here. You're going to have to do a little bit more work, but if you put the zero line there, it's a little bit more work on the front end to save yourself some heartache on the back end. So give that a shot once you get more comfortable with this. The next thing we talk about is work. So we just learned that energy is conserved as long as nothing comes in and messes with it. Well, work is the thing that would come in and mess with it. You do work on a system when you're taking energy, or when you're putting energy into the system or taking it out. So think about energy like money. If you've got some money, then you can spend that money by putting it into another system. So maybe at Target or online or anything like that, you can put money into their system. Or if you're working, then they can put money into your system by paying you for your services rendered. A system is kind of like your family. If you give your brother $5, then your family still has the same amount of money. Or if your brother gives you $50, then your family still has that same money. That's energy transferred inside the system. But as soon as one of you gives it to some other store, then that money leaves the system, and that store has done work on you because they've taken money from you or taken energy. So work, the big thing to remember is the work due to something is equal to the parallel force times the displacement. So this is actually a very, very important concept right here, the parallel force. You're only really doing work on a system if you're applying a force that is parallel to the displacement of the system. So as I'm pushing some sort of box, if I push it to the right and it moves to the right, I am doing work on the system. But if I push the box down and it moves to the right, then I'm doing no work because none of my force is parallel to the system, or sorry, is parallel to the displacement. We're going to get a little bit of that into the practice problem in just a moment. But that is very important to remember, is that the force that you plug in here has to be parallel to the displacement. So go ahead and take a moment to read this problem just to get yourself acquainted with it. See if you can draw yourself a little picture of it, because that's going to be the first thing I do. Alright, so I'm going to go ahead and draw that picture. I've got a box being pulled at a 22-degree angle. And now we've got a tension in the rope, which is 30 newtons. How much work do the following forces do if the box is pulled 75 meters? So I know that my displacement is 75 meters. I know it doesn't say it in there, but I'm going to go ahead and assume that it's to the right, just to keep my life simple. I should have put in there that it's to the right. So for part A, we've got the work due to tension is equal to the tensional force that's parallel times the displacement. So as we look at this, our tension has two components to it. And this is the thing that always gets people with forces, is that this tension is pulling up and to the right. So I've got two components of it. Here's Ty, here's Tx. Since the box is moving to the right, the one that's parallel to it is Tx. So what I care about right now is figuring out what is my x component of tension. And I do so by using right triangle trig. So breaking it up into that vector, here's T, here's Tx, and here's Ty with a 22-degree angle. We know from the problem that T is 30 newtons, which means I can use SOHCAHTOA and figure out that the cosine of my angle is equal to adjacent Tx over hypotenuse T. Doing a little bit of rearranging, we end up with the tension, which is the hypotenuse, times the cosine of my angle equals Tx. So I'm going to go ahead and plug that in over here and say that the work that the tension does is equal to that tensional force times the cosine of theta times my displacement. So let's go ahead and plug in these numbers for it. We've got the work due to tension is equal to 30 newtons times the cosine of our angle, which is 22 degrees, times the displacement, which we said was 75 meters. Plugging all this into the calculator, because we're hitting that sine, cosine, or tangent button, we have to make sure we're in the right mode. Since it's 22 degrees, I'm going to make sure my calculator is in degree mode. So 30 times the cosine of 22 degrees times 75 tells me that the work due to tension is 2,086.164, and the unit for work is joules. So there is the work that is applied by that tensional force. Part B is actually going to be much easier, and you'll see why in just a moment. So part B, we're looking at the work done by gravity, or the force of gravity, so we can also say weight, keep that in mind. So the work done by the weight is going to be the parallel component of weight times the displacement. Now, our box is being displaced to the right, and the force due to gravity always points down. So there is no parallel component to it, which means my work due to gravity is simply 0 joules. So work is all about adding energy to the system or taking it out of the system. In this case, we have to overcome friction in order to pull that box. And in a real life situation, it would be things like giving a push to an object or giving a pull to an object or something like that. Which brings us to our last section, which is power. So power is simply the change in energy over the change in time. So this is how the energy changes and how fast it changes. And without further ado, let's just go ahead and jump right into a problem. So go ahead and take a moment to pause and read this. All right, so as we look at this, we are going from a compressed spring that's carrying a BB, so this is my initial position, to a final position of an uncompressed spring, and then the BB's being shot out forward. I don't know why it got so much bigger, but we'll keep it. So what we're asking is, what's the average power that the spring applies? So we're only really looking at this spring. The spring is going to go from compressed to not compressed. So we're going to figure out how much power that spring applies, and it turns out the power is only that, the energy is only that elastic potential energy. So it goes from having potential elastic to not having anything. In a perfect ideal physics world, that's kind of what we're looking at. Yeah, there's still little things left and right that it's moving, it's not perfectly still, but we're going to go ahead and discount that and say all of that energy gets taken out. So the average power that the spring applies is what we're going to do is take that energy. So elastic potential is 1/2 kx squared, and that would be our energy. The amount of time that it takes is going to be that 0.1. So to get this answer using that previous equation is all we have to do is say 1/2 kx squared over my amount of time equals my power. I'm going to make my life a little bit easier and pop that 2 in the denominator. So kx squared over 2t equals my power, where k is 400. My x, I gotta be careful, and I gotta make sure that I am changing. It's 5 centimeters, but I want it in SI units, so it is 0.05 meters, 0.05, all over 2 times 0.1, and I end up with 400 times 0.05 squared. Divide that by 0.2, gives us 5 joules. Oops, sorry. Power is not measured in joules. Power is measured in watts. So 5 watts of power is given by that spring. So we've done a quick example of all of those different problems there. Let's go ahead and do one more practice problem that basically takes everything we've learned and mushes it into one problem. So go ahead and take a moment, just as always, to read this question and see what you guys can figure out from it. So if you haven't finished reading, go ahead and pause it because I'm going to jump right in. We've got a skateboarder, and please pardon my drawing. I am not Picasso, but we'll deal with it. So here's the skateboarder. He starts from rest, so here is my initial. And then he's applying an average force of all those number stuff, and we end up moving. So he goes from not moving to moving. And again, just like the BB, he ended up getting faster, or sorry, getting larger. But whatever, his head got smaller. Here is my final position. And what I want to do is I need to figure out what speed we have at the end of that 25 meters. So in this case, he is applying power, or he is doing work. The skateboarder himself, he starts with an initial velocity of 0, and then he is expending some of that chemical energy. So his body is doing work on that system. So what we cannot say is that our initial energy equals our final energy, because it doesn't. What we've done is we've done work on the system. So we can say that the work that the person does plus our initial energy equals our final energy, because now they're adding energy to the system, and that energy added at the beginning ends up going and turning into some other form of energy. So let's go ahead and do what we've been doing, which is work is equal to, and now I've got KEI plus UGI plus UEI equals KEF plus UGF plus UEI. And I'm going to go ahead and plug in anything that was 0. So at the beginning it says that he was at rest. We also need to set a 0 line. Well, since we've got a flat parking lot, let's just go ahead and set the ground as 0, because he's not changing his height at all, which means that if we set this line as 0, then not only will his initial gravitational potential be 0, but so will his ending gravitational potential. We also don't have any sort of springs or anything like that messing with it, so that's 0. At the end he is moving, but there is no spring or rubber band or anything like that into the system, so really it boils down to a very, very simple equation. W equals KEF. If we remember from the last bit, the parallel force times the displacement is equal to our work, and the kinetic energy is 1/2 mv squared. Again, I should have explicitly put in here that the average force that they apply is horizontal, but that's just me. I ended up making a mistake, and to be honest, I'm telling you now, in the future, problems should have that it's parallel to that displacement, but here we can just assume that he does apply that parallel. So let's go ahead and rearrange and get our variable by itself. We ultimately need to know the speed at the end of the 25 meters, so we're trying to find that velocity there. So F parallel times displacement. Let's go ahead and multiply both sides by 2 equals mv squared. Divide both sides by m. And last but not least, take the square root. It's 2 F parallel times displacement over m gives us our velocity there. Plug in a little bit of numbers, and we'll end up with the square root of 2 times his force applied, 75, times the displacement, which is 25, all over the mass, which is 80 kilograms, which gives us a final velocity of, and be careful with those square roots and parentheses and all, I end up with 6.8, that's not an 8, 0.847 meters per second, and that is my final velocity. So that answers the first part of the question, is how fast was he at the end? He was 6.847 meters per second. Last thing we need to figure out is how much power he applied. So the power is the change in energy divided by the time. Well, the change in energy, we started with 0. We ended up with however much work he put in. So there's a couple of different ways that I can do this. The way that I'm thinking of doing it right now is I know that I can do a little bit of rearranging, and I know that the change in energy is equal to EF minus EI, and the change in energy that happens if I rearrange this is actually just the work, which if we think about it makes sense. Work is when you put energy into a system or take it out, so that is your change in energy. So it makes sense that we can write our power equation as work over change in time as well. So how much work did he do? Well, the work was equal to the force times displacement, and the amount of time that we went through is listed in there, which means we're just plugging in some numbers here. 75, make that a little clearer, 75 times 25 divided by 2 means that we are looking at 75 times 25 divided by 2. That's not 75 times 25. It helps if you plug it into your calculator correctly. The average power that this person applies is 937.5 watts of power, which is actually not unheard of. That seems like a very reasonable answer for him. He started moving pretty quickly at the end of that time period. So there is your quick overview of work, energy, and power. Energy is something that can be transferred between things. As long as nothing's messing with the system, it's all conserved. If something is messing with the system, that means it's doing work. And the amount of work you do over time tells you how powerful something is.